So today we are going to start lecture 7, and this is the first of the one-dimensional search methods. So like we discussed before, for most practical optimization problem, you do not have an explicit function f of alpha. Therefore, a numerical method must be used to find this particular minimum value where you have some value of alpha which minimizes the function f of x along the direction d of k. And these one-dimensional search methods essentially find the minimizer of a function on the interval alpha subscript L, alpha subscript U. So essentially these two numbers here form the lower bound and the upper bound on the problem. And one-dimensional search methods presume that the function is unimodal, and we have seen that this is true because f dash at 0 is less than 0, and therefore the function has a particular shape which you have seen before, and therefore the function keeps going down, and at certain point it reaches a minima point, and after that the function may go up. Now a unimodal function is defined as one which has a unique minimum in the particular region we are interested in. And this is in contrast to something known as a multimodal function which has more than one minimum point. Now the unimodal approximation is reasonable if we have selected a descent direction, because essentially if you are in the descent direction, then if we go down by a certain value in this direction, we should be reducing the function and hopefully reaching some kind of minimum point. Now one important thing we do in these kind of one-dimensional search methods is that we bracket the minimum point, and this bracketing is done between the two bounds of this particular set, and this particular distance here between alpha u and alpha l is known as I, the interval of uncertainty. So this is a very important concept in one-dimensional search, and all these algorithms essentially try to bring down this particular number I to an acceptable level, and the algorithm keeps going on till this I is brought down to a low level. Now essentially if we plot a general curve of f of alpha with respect to alpha, you get something like this, and this is going to have some minimum point at some place here. So again, this is the alpha subscript L, the lower bound here, and the alpha subscript U, the upper bound here. And essentially when you have discovered these two bounds, you have bracketed the minimum. So these bounds are somewhere in between which the minimum point lies, and the distance between this alpha L and alpha U is denoted by I. Now the aim of all these one-dimensional search methods is to bring down this value of I until it is smaller than a certain small number. So let us say I is less than some very small number here, which we will call by epsilon. Now once the interval has been sufficiently bracketed, the minimum point of this function f of alpha can be obtained as the midpoint of this particular closed interval. So essentially alpha star is half of alpha L plus alpha U. So this is how these search methods proceed. They essentially keep bringing down the interval I, and when the interval I has been brought down below a small number, say this number may be 0.1 or it may be 10 to the power minus 6 depending on the level of accuracy which you need for this particular problem. So again, that level is selected based on the particular type of method which you are using for the search direction. So there are some methods such as conjugate gradient method which would require a certain level of search direction, and then there are methods such as the quasi-Newton methods which may require a different level of search direction in the unidimensional search, and you need to exactly choose the methods to go with your one-dimensional search. Now all these methods which are there, which essentially focus on reducing this interval I, are known as the interval reducing methods. And they are also sometimes called the zero order methods because gradient information is not being used here, and therefore these methods only rely on function value. So again, this is some nomenclature which is widely used in optimization in terms of the derivatives which are needed for a particular method. And so today we are going to discuss the simplest such method, the equal interval search. And in this method, what we do is that we take the function, and since we know that this function is unimodal, we essentially create a uniform grid here. So essentially we choose some small number delta, and so we find the function value here. Then we take 2 delta, 3 delta, all this way and so on. Now, if we want to generalize this concept, we call some points as q delta, q minus 1 delta, and q plus 1 delta. And we are essentially looking at these 3 points where the function changes. Essentially, the function is going down and then the function starts going up. So essentially, we want to capture 3 points where this particular phenomena happens, that the function starts going up. And once we have captured this location, we can say we have bracketed the minimum point to this particular region between q minus 1 delta and q plus 1 delta. So let us say we start with a certain interval and divide this into a uniform grid where each of these intervals is of size delta each. Now we calculate the value of the function at all these points on the uniform grid where delta is some small number. So maybe you start with a value such as 0.1 and then go further down. So these points are then given by delta, 2 delta, 3 delta, q minus 1 delta, q plus 1 delta, and so on. Now we keep comparing these values at 3 successive points. So for example, at delta, 2 delta, 3 delta, at q minus 1 delta, q plus 1 delta, and so on. So what's going to happen is that 2 possible scenarios may exist. One is that the function value at q delta is greater than the function value at q plus 1 delta. And if this is the case, then the minimum point has not yet been surpassed. The second possibility is that f of q delta is less than f of q plus 1 delta, then the minimum point has been surpassed. So if the point number 1 is true, then you keep calculating the function further on till this point 2 becomes true. That means you essentially keep going till this condition is satisfied, that your q delta is less than q plus 1 delta. Now if 2 is true, then the minimum is between q minus 1 and q, or q and q plus 1, and this I will explain by a graph very soon. So essentially this is known as bracketing of the minimum point in one-dimensional search, that we keep going like this and then we have found a point here where the function was decreasing, and then lo and behold it has started to increase. So essentially this is the point where we bracket the minimum, and therefore from this enormous set which we had, we have bracketed the minimum down to these 3 points. Now you can take a look at 2 possible cases why you have to consider q minus 1 and q plus 1 and not just q and q plus 1. So that's a question that comes in the mind of many people. So let's look at both scenarios. So what has happened is fq plus 1 is greater than fq. So you can see here that function value at q plus 1 is greater than fq. But the minimum may be here. And the second situation could be same thing applies here, fq plus 1 is greater than fq, but as you can see here, the minimum value may be here. So basically what we then say is that minimum would lie between q minus 1 and q plus 1. So essentially we will denote the minimum by this value alpha superscript star, and this could be here or this could be here, and so essentially we have then bracketed the minimum point. So the minimum point is now bracketed between q minus 1 and q plus 1, and therefore alpha lower bound is q minus 1 delta and alpha u is q plus 1 delta, and if you subtract these two numbers you get that I is 2 delta. So essentially from this you can see that the value of I, or how low it is, would be directly proportional to delta. Now, if you were to start with a very small value of delta, then you have to do a huge number of function calculations before you zoom into the minimum point or you bracket the minimum point. So therefore, what is essentially done is that you start with a coarse grid or a relatively large value of delta, and you quickly bracket the minimum point. And once you have done that, you can further split this particular bracket into finer grids and keep doing this till you reach the minimum point. So essentially you loop across this particular concept and you keep going further and further down into the minimum point. So you can see that this particular procedure is relatively easy to program on a computer, and you can easily write a computer code for it. Now we have discussed the method with the point alpha bar as a requirement, but you really don't need any of these alpha bars here, which is, if you remember, alpha bar was the end point between 0 and alpha bar where alpha was taken. The minimum is done between q minus 1 delta and q plus 1 delta. So therefore, all you need to do is you need to select this particular delta, and once you have selected this, you can continue going down this interval search. So appropriate selection of delta is going to be very important, and this is going to be a challenge for most situations because, as you can understand, all functions do not have the same level of scaling. So one of the important things is that you need to scale your variable such that the numbers are reasonable. So there may be functions where x has values ranging from 0 to 1 million, and there may be functions where x ranges from 0 to 10 to the power minus 6. So again, the level of discretization which you choose in these particular functions is going to be a different, and therefore it is important to choose this delta depending on the value of the function. So again, this is something to keep in mind. So this was a basic outline of the equal interval search method, and this is probably one of the simplest methods you can use for doing the one-dimensional search, and conceptually it is very simple. It is also a safeguard method, as we can see later, because there are more powerful methods which can be used to find the minimum point here. But what is good about this particular equal interval search method is that it is a pretty fail-safe and robust method. So because its concept is very simple, it will generally work very well for most problems. So again, that is the end of lecture 7. Thank you very much for listening to my video, and I'll see you in my next video.